So up until this point we've talked about the kinematics of rotating objects, and the next logical step is to talk about the energy associated with rotating objects, much like we did with the translational motion. So you know that an object that is rotating has kinetic energy. If you ever grabbed a bicycle wheel that was rotating, it essentially gave some of the energy to your arm and probably snapped it pretty good. So an object that is rotating has kinetic energy. That kinetic energy is because it is spinning. We know in the translational sense we write our kinetic energy to be 1/2 mass velocity squared, so that's translational kinetic energy. We can also write the kinetic energy of a rotating object as looking at the sum of all of the tiny little masses that an object is made up of, as well as their velocity. What we can do then is we can say, well, we know how the velocity is related to the angular velocity, plug that guy in and get the total kinetic energy of the object. Turns out that we can write then our rotational kinetic energy to be this quantity right here, 1/2 I omega squared, where this I is going to be the rotational mass, and I'll talk about that quite a bit more in the next couple of slides, and this omega squared is simply the angular velocity that we're already familiar with. This looks very, very, very similar to our expression of energy for moving objects. So if you're familiar with applying this equation up here, this equation right here is really very similar. 1/2 I omega squared, I is rotational mass, omega squared is angular velocity, 1/2 mass velocity squared up here. An object that is both moving and rotating is going to have both types of energy associated with it, and we know that it is going to move and rotate about its center of mass. So we can write the kinetic energy of an object that is moving and rotating simply down here, 1/2 mass velocity squared at the center of mass, plus 1/2 the moment of inertia, or the rotational mass, multiplied by the angular velocity squared. So here I want to talk about this beast that I called the rotational mass on the last slide. It had the symbol of I. It also has another name. It's also called the moment of inertia, and it's related to an object's mass as well as its distribution of the mass. And really it's similar to the mass in the translational sense in that it's how much an object is going to resist being rotated. You kind of know intuitively that it's going to depend on, one, how massive the object is, but also how far away it is from you. It's much, much, much harder to rotate something that is far away from you than something that is very close to you. If we consider just some point particles, then the moment of inertia is simply going to be the sum of all of the masses of these point particles multiplied by how far away they are from the axis of rotation, and that's going to be a squared quantity. So this radius right here is not going to be the radius of an object, it's going to be the distance from the axis it is rotating about. And this expression right here is good for two particles, but if there was a third, fourth, fifth, so on and so forth, you'd simply add them on. Following example 9.6, we can go ahead and do a quick calculation of this guy. So we're going to say, okay, we have three particles here. We've got A, B, and C. They all have some masses that are associated with them. Let me choose my axis to be going through disk A, and I want to calculate what the moment of inertia is, how much this system is going to resist being rotated about A. So I'm going to say my moment of inertia is going to be the mass of A multiplied by the radius of A, the distance of A from the axis of rotation. You can kind of see that's going to be 0. So mass of B, the distance that B has from the axis, and lastly mass of C multiplied by the distance of C squared from the axis of rotation, we can see that A has the axis passing through it, so the distance to the axis is going to go ahead and be 0. So we're left with B and C, so we can say that the moment of inertia, or the rotational mass, is going to be the mass of B, so 0.1 kilograms. B is located a distance of 0.5 meters away from the axis, so 0.5 quantity squared. And I'm going to add as well mass C, 0.2 kilograms. And this guy is located 0.4 meters away, so that's going to be squared. You peck all that into your calculator and you're going to come up with 0.057 kilograms meters squared is going to be the units of this guy. The kilograms comes from the masses, the meter squared comes from the radius squared. Something to note, and you can follow along in the book, example 9.6, is if we chose our axis now not to be going through A, but we can go ahead and we can choose our axis to be right here through B and C, then we will write the same expression up here, it's the sum of all the masses and the radius squared, but the radius of B is going to be 0, the radius of C is going to also be 0. We only have to deal with the mass of A, and kind of intuitively you would say, well, I know that it's going to be probably easier to rotate this guy about this axis B and C than going about through disk A, and you can convince yourself of that. Of course, the world doesn't necessarily exist of single points of particles that are rotating. We're going to have objects that are rotating. Suppose we had a disk with mass m and a cylinder with the same mass m. You would kind of think, well, I know that this one is going to be harder to rotate. The reason about an axis going through its center here compared to that one, the reason for that is because this guy here has its mass spread out over a much larger radius than this guy. So we can write this same expression here for all these tiny little chunks of mass all located at a given radius, and we can essentially sum all those up and come up with the moment of inertia of a whole bunch, or come up with the moment of inertia of bodies that are rotating now, not just point masses. It turns out that this has been done, so we don't have to go ahead and redo that. Very important table to have in your mind and to be able to use. Here we have the moment of inertia or the rotational mass for a whole bunch of different bodies. We have hollow cylinders, solid cylinders. Solid cylinder would also be a disk, and so on and so forth. We can also see, even a slender rod that is being rotated about its center is going to be different than that same slender rod that is now being rotated about a axis over here. And you would think, okay, I know that it's going to be much harder to spin this slender rod about its end than through its center, and the moment of inertia is going to bear that out. Because we know that this quantity is defined to be the sum of all the masses multiplied by the radius squared, we can actually add masses to the rotational masses of known objects. For example, if you had a merry-go-round and you treated that merry-go-round as a solid cylinder or disk, you know what the moment of inertia of that guy is going to be. Suppose you decided to plop two children, each of mass m, located at the radius r away from that. what we can do is we can say, well, I know that the moment of inertia is going to be the sum of all the masses and their location from the axis of rotation. I can simply break this up into the masses of the merry-go-round, so I would just call that disk for simplicity, plus the sum of the masses and the radiuses squared of the children. I can look this one up in a table. I know that that one is going to be 1/2 big mass multiplied by the radius squared, and I treat my two children as point masses, each with mass little m located at radius big R away from the center. So here I'm going to have two children with mass m and located at radius big R away from the center squared. So now I've gone ahead and I've calculated my moment of inertia for a body that I knew a little bit about, and I've modified to meet my needs. Let's take a look at example 9.7 and try to relate some of the things I've been talking about to things that we already know. In this problem, we have a pulley, and a force is going to be acting on that pulley. It's going to get it rotating. We know that the force is 9 newtons, and it's going to act over a distance of 2 meters. What we can do is we can say, okay, I know that that force did some work spinning that pulley up, and all of that work is going to be transformed into now kinetic energy of the pulley. So let's figure first out how much work I did, work being the force dotted with the displacement right there. The force and displacement act in the same direction. The angle between them is 0, so I can simply write that as the product of the two of them. Force being 9 newtons, the distance being 2 meters. So I come up with 18 Newton meters, or 18 joules worth of work. I know from the work-energy theorem that I can write the energy beforehand in potential form and in kinetic form, add that to the work that was done by other forces. I'm going to end up with the potential energy afterwards and the kinetic energy afterwards. Now we know that there is no potential energy in this system, so these terms are going to go to 0. And I also know that the wheel started from rest, so there was no kinetic energy to start with. What I'm left with is the work that was done by the pole, work done by others. I'm going to call that work done by the pole now. It's going to be equal to the kinetic energy at time 2, which is now going to be 1/2 multiplied by the rotational mass and angular velocity squared. That's what I'm interested in solving for. How fast is that guy going after that pole acts on it? So it's a simple matter of saying, okay, I know that these guys are related. I can solve for the angular velocity. That's going to be 2 multiplied by the work done by the pulley. Divide that by the rotational mass quantity squared. Now what exactly is that rotational mass? I don't know that quite yet. I can go to the table in the book and I can say I'm going to treat the pulley as a solid cylinder or disk, so I can figure out what my rotational mass is going to be. It's going to be 1/2 the mass of the disk multiplied by the radius of the disk squared. Here the radius of the disk is going to be half of the diameter, so 0.06 is going to be my radius. I know the mass of the disk, so 1/2 multiplied by 50, 0.06 quantity squared, and I'm going to come up with 0.09 kilograms meters squared. So all I have left to do is to plug all of these quantities into my expression for angular velocity. I'm just going to do that down here for space limitations. So 2 times the work that was done, that was equal to 18 joules. And divide that by rotational mass, 0.09. Go ahead and we pack all that into our calculator, and we're going to come up with 20 radians per second. There we go. I want to come back for a second and talk about this rotational kinetic energy and what it means for conservation of energy. If I have a ramp and I place several different objects on top of that ramp, then they're all going to have the same amount of potential energy available to them. That potential energy is simply going to be the mass of that object multiplied by the gravity multiplied by the height h that I've lifted them up. Now we'll say all of these objects have the same mass to them. However, their mass is going to be distributed differently for various things. We're going to have a hoop, we're going to have a sphere, and we'll go with a box that does not rotate. All of that kinetic energy, all that potential energy is going to go into kinetic energy, which can be in the form of rotational kinetic energy, or it can be in the form of translational kinetic energy. So an object that is not rotating, for example, the box, all of this potential energy is going to go into the translational speed of that box. It's going to go down quite fast. However, as soon as we start worrying about rotation, for example, having a sphere, then some of this limited potential energy is now going to go into rotating the object. So the translational speed is going to be lower. Obviously, the rotational energy is going to be I omega squared divided by 2, so this rotational mass is going to determine how much energy the rotation is going to suck away from the translational velocity. So a hoop, where all the mass is distributed on the outside of the, or at the radius r away from the center, is going to have a much larger rotational inertia than the sphere. So the amount of rotational energy that is taken up by spinning that ramp is quite large, and it is not going to have a very large translational velocity. So the hoop is going to go down much slower than the sphere, and which is still slower still compared to the box. Example 9.8 is going to highlight this, but using a pulley system. If we consider a mass that is being hung from a pulley, now the pulley has mass. Now we need to worry about that. All of the energy of this system is going to be in the form of potential energy, the fact that this mass has some height associated with it. So we could say beforehand that the energy is going to be the little mass multiplied by gravity multiplied by how high it is. If we consider what happens just before the block hits the ground, the block is moving, it has some velocity. The block is going to have some kinetic energy, and that's going to be 1/2 the little mass multiplied by its velocity squared. The pulley is also rotating. It now has some energy associated with it too. We write that energy as 1/2 I omega squared. What we can do then is we can say, well, I'm going to look up the moment of inertia for a disk or a pulley. So 1/2 the mass of the pulley multiplied by its radius squared. And something else that I know is I know the relationship between the linear velocity and the angular velocity. I can write the angular velocity to be equal to the linear velocity divided by the radius of the pulley. So I can substitute these two guys into my expression up here and get everything in terms of a linear sense. So I'm going to say that the kinetic energy is going to be 1/2 the little mass multiplied by its velocity squared plus 1/2 the mass of the 1/2 multiplied by the moment of inertia, which is going to be the 1/2 of the big mass of the pulley multiplied by the radius squared, and then omega squared is going to become the velocity divided by the radius quantity squared. And we can see that some of these radiuses are going to cancel out, and what we can do is we can simply rewrite this guy now. The kinetic energy is going to be 1/2. I'm going to pull out a 1/2 here, as well as a v squared. So 1/2 v squared, little mass plus the big mass of the pulley divided by 2. So here I have an expression for the kinetic energy afterwards. Here I have an expression for the potential energy beforehand, and the total amount of energy available to this system is always going to be a constant. So I can set these two guys equal to each other, and I can say, hey, I can figure out the velocity of the block just before it hits the ground. I can figure that v out. So I'm going to set the potential energy equal to the kinetic energy, or mass times gravity times height, is equal to 1/2 velocity squared, and then the little mass, and then 1/2 of the big mass. So I multiply both sides by 2, I divide both sides by this quantity, and I end up with an expression for the velocity in terms of the height of the block and the mass of the block and the mass of the block and the mass of the pulley. So it's going to be 2 mass of the pulley, or mass of the block, gravity times height, divided by the little mass plus the big mass divided by 2 down here on the bottom, and that square root covers everything. While we're on the topic of energy, let's talk about gravitational potential energy for objects that are large and they have size associated with them. So if I have some object and it's got its mass kind of distributed throughout it, maybe it's more dense over here, then I know that the center of mass might be more towards this side than towards that side over here. It turns out that when we talked about center of mass, we said that all of the rotation, translation, so on and so forth is going to occur about that center of mass point. It turns out that the potential energy, the gravitational potential energy for such a body, is also going to behave as the mass multiplied by the gravity at the center of mass. So if that center of mass is some distance away from the ground, then we write the gravitational potential energy available to it as the height to its center of mass. So the last thing I want to talk about is a very, very important tool. It's called the parallel axis theorem, and what it does is it lets us relate the moment of inertia at the center of mass to the moment of inertia about some other axis. Very frequently we know what this moment of inertia about the center of mass is. We may want to rotate a body through a different axis. What we can do is we can say, if I have this object right here, we know we're following example 9.9, so we know rotate the moment of inertia about the center of mass. That's a given to us, and it says, okay, I want to now take this hinge and I want to rotate it about this axis over here. It turns out that we can write what the moment of inertia about that axis P is simply by being the sum of the moment of inertia about the center of mass plus the mass of that object and the distance between the axis of the center of mass and the axis P that we're considering here. So that's going to be my D right there. Very, very, very important theorem to know and be able to use. If we consider a disk, for example, and I say, okay, I know what the moment of inertia about the center of mass of that disk is. I can look it up. It's 1/2 mass radius squared. Now I say I want to take that disk, and rather than rotate it about its center, I'm going to spin it around this axis over there. Then the parallel axis theorem says, okay, I can say my rotation about this axis, I'll call it P just for simplicity, is going to be first the rotational, or the moment of inertia about the center of mass, 1/2 mass radius squared, plus the mass of the disk, m, and the distance between the axis P and the center of mass is also going to be the radius, and that's going to be squared. So I'm able to use a moment of inertia that I know to figure out a moment of inertia about some other axis.